Hello, this is Mr. Stein, and in this video we are going to go through example problems 1 and 2 of section 5.6, Properties of Linear Relations. Once you're done this section, you should be able to determine if a relation is linear or not, either from a table of values or from the graph. Graph two variable equations and relate the slope of a graph to the rate of change. All right, let's look at example number 1. Which table of values represents a linear relation? Justify your answer. We're going to do this two ways. We're going to do this from the table of values, and we're going to graph it. So our first one, the relation between the number of bacteria in culture, N, and time. Well, let's take a look. Every time our time goes up by 20 minutes. That is constant. Now, if our number of bacteria goes up a constant amount each time, then it will be linear. If it doesn't go up a constant amount each time, it won't be. It goes up by 1, by 2, 4, 8, 16. These are not constant amounts compared to these amounts. This is not linear. No constant rate of change. Now let's graph this one to see how it looks, because we need to practice graphing. Our horizontal axis is our time. Our vertical axis is our number of bacteria. Our horizontal axis, we need to go up. We start at 0. And now I just put easy numbers in. I put 20 here, 40, 60, 80, 100, 120, and I think that's as high as I need to go. And I'm going to jump this guy up, my n, by 4. So 4, 8, 12, 16, 20. I don't need to mark every one. People should be smart enough to figure out how big each gap is, just from a few. All right, so at 0, it's at 1. That's right about there. At 1, it's at 2, or sorry, at 20. Let me pull my eraser out here. At 20, it's at 2. At 40, it's at 4. At 60, it's at 8. At 80, it's at 16. And at 100, it's at 32. So this is 20, 24, 28, 32 right here. It's easy to see from this graph that this is not a linear relation. This is not linear. It's not in a straight line. It's in a curved line. Curved line is not linear. This is an exponential function. All right, let's look at the next one. The relationship between the amount of goods and services tax charged, T, and the amount of purchases. So the first one, you purchase $60, you pay $3 tax. You purchase $120, you pay $6 tax. Now we can see our amount of purchase is going up by, not 16, try 60. 60 each time. That's good. That's constant. It goes up by 60 each time. Our tax is going up by 3 each time. We can tell right away that this is linear. It has a constant rate of change. We can also determine the slope of the line from this graph. The rise over the run. The rise is quite simply this number over here, and this is our run. So this graph goes up $3. So the tax amount goes up $3 for every $60 you spent, which is equal to 1 over 20, or 5%. So this is a 5% tax. Now let's graph this. A, the amount we spend, is our independent variable. That's what we choose. The amount of tax we get charged is based on the amount we spend. Now, 0, 10, and up to 20. So we need to go up to 15. So I'm going to count up by 2's there. And again, I'm going to just be lazy. 60, 120, 180, 240, and 300. So it's at $60, you pay $3 in tax, which will be right there, $3. At 120, we pay $6 in tax, which will be right there. Every grid space is 2 vertically. At 120, it's $9. That's right there. At 240, it's $12. That's right there. And at 300, it's $15. That's right there. Now, if we spent $0, we would also spend $0 tax dollars. And you can see all of these points line up on a nice straight line. And the slope of that line is 1 over 20, or 0.05, or 5%. All right, example 2. Which relation is linear? Justify your answer. A dog sled moves at an average speed of 10 kilometers per hour along a frozen river. The distance traveled is related to time. So let's build a table of values for this. Time is going to be our independent variable, and distance is how far we go. At 0 time, we travel 0 kilometers. After 1 hour, we've traveled 10 kilometers. At 2 hours, we've traveled 20 kilometers. And at 3 hours, we've traveled 30 kilometers. This 10 kilometers an hour is our rate of change. And it is constant. So you can see here that this goes up by 1, by 1, by 1. This goes up by 10, by 10, by 10. So yes, this graph is linear. We have a constant rate of change. Now let's quickly look at letter B before I run out of disk space. So here we have the side length of a square, and here we have the area. So here's our square. We have our area. We have our length. Our area is equal to the length squared. So if we have a length of 0, we have an area of not 2, 0. If we have a length of 1, our area is 1 times 1, or 1. If we have a length of 2, our area is 2 times 2 is 4. If we have a length of 3, our area is 3 times 3 is 9. When we look at this, we're going up by 1 each time. When we look here, we're going up by 1, by 3, by 5. This is not a constant rate of change. Not a constant rate of change. This is a curved function. It's a square function, and so it is not linear. All right, I hope this was helpful for you. If you have any questions, please put them in the comments below or send them to me directly.